All right, we are back to our BC Calculus integration techniques topic. Today's subject is arc length. This is actually our last little subject within topic 1. So the next couple days are going to be review and then a test. Your test will have 2 parts. One part's going to be multiple choice, one part's going to be free response. But let's get to it. So, the idea behind arc length is we're going to use calculus to calculate the length of a curved curve. Just of a curve, I guess I could have said. In the past, like in geometry, you've gone through and you've had to calculate lengths of lines, and that all relates to the Pythagorean Theorem. If you wanted the length of this line, you find how far up, how far over, Pythagorean Theorem, and go from there. Arc length really uses the exact same idea. So, just a reminder, if you're given 2 points and you want to find the linear distance between them, you should use the Pythagorean, remember that extra a at the end, Pythagorean theorem solved for c. A squared plus b squared equals c squared, square root to get that c is going to be the square root of a squared plus b squared, where c is going to be the length between your 2 points. The same idea applies to curves, because remember, any curve, as long as it's differentiable there, if you zoom in far enough on a curve, it's going to resemble a line. And you can kind of see it here. I mean, if we take this piece that's represented by x1, it is clearly curved, but if I zoom in far enough, and again, I can't quite zoom that far, it really starts to look pretty darn linear. It looks like a straight line. Of course, zooming out, we can see it is curved. So, the idea of zooming far in on a curve and having it look like a line is the concept known as local linearity. Okay. Now, what we're basically going to do for this is we're going to split up a curve into multiple different segments. And then we're going to add up each segment, and when we add up each segment, we'll of course have the total length. Now, how large of each segment is an interesting question. We'll get that in a second, but for now, let's go ahead and just look at the length of the curve S1. Well, S1 is going to have almost perfect linearity here, right? We can see this line down here. It's not quite perfect, but it's pretty darn close. And so if we assume that it's the same as that dashed line right here, then we can go ahead and use our change in x and change in y to find the length of that curve. Now remember, of course, the change in x, if this is like b and a, the change in x is b minus a. It's the distance between those 2 points, right? And then our change in y is, of course, the change in the y values up here. Maybe you could think of it as something like f of b minus f of a, yeah? Right? That's where we get our slope formula. Okay, but either way, if we wanted to go through and we wanted to find s sub 1 is like c in this case, so it's going to be found by just doing the square root of, let's do it this way, let's do the delta, no, I do x first, we'll do x. So we're going to do delta x sub 1 squared plus delta y sub 1 squared. So basically a squared plus b squared equals c squared. Nothing terrible. And that would find us s sub 1. Of course, we eventually would have to find each piece of this curve, the next piece and the next piece, and add them all up until we get to the length that we're trying to find. Now, if you add up all of those pieces to get L, where we're going to use capital L to stand for our arc length here, you'd of course do S1 plus S2 plus all the way up to S sub n, where S sub n is the last piece of the curve that you want to stop at, right? That's your stopping point there. Of course, it's a little tedious to write out S1 plus S2 plus S3 and so on and so forth, so we of course can notate this using our sigma notation, right? We want to sum up, and this 1 is going to take the place of k, that forms S sub 1, and then after k equals 1 it becomes 2, that takes the place, and that's the next one. Sigma, our capital Greek letter here, means sum everything up, and where do we stop summing? Well, we stop summing at whatever n is. Okay. Now, of course, we know a formula for s sub k too. For any s, in the example up here, s sub 1 was delta x sub 1 squared plus delta y sub 1 squared, then we can of course say that s sub k is the same thing as this piece, where whatever k you're looking at here, maybe this was 1 like our example up above, it is the same in all of these, and then of course that would be your first piece of the curve. And then k ratchets up a notch, and now we're at k equals 2, and it'd be delta x sub 2 squared plus delta y sub 2 squared, and so on and so forth. So now we have a nice formula here in terms of x and y. But we're not done yet. We're going to try to make this easier. One of the issues of this formula is that it has both x and y in it, so we're going to see if we can simplify that, and we do it with some clever factoring. In particular, we're going to divide out a delta x sub k squared from each of these. Now, we can't really divide something out, because if you divide something out, you'd have to do it to the other side as well. Instead, we're going to factor this piece out. So we're going to take that and we're going to move it out front. And when we do that, of course, this becomes 1, right? That's where the 1 comes from. This doesn't simplify at all except for moving the square to the outside. So that's where this next piece comes. It comes from our Pythagorean theorem, but with delta x sub k squared factored out. From here, can we simplify further? Well, notice that we have two terms multiplying, and whenever you have two terms multiplying, you can distribute the square root. So maybe that gives us the square root of the first piece and the square root of the second piece. The square root of delta x sub k squared, well, in this case, the square root cancels the square. And if you're like, what do you mean in this case? Well, really the square root of something squared, the square root of x squared is not x. The square root of x squared is the absolute value of x. But as long as your x's are positive and delta x is going to be positive, it's a distance, then we can say it's equal to just x. So same thing here when we do the square root of delta x sub k squared, it is just delta x sub k, moved it out front there. And then the inside we can't distribute further, there's a plus preventing that distribution of the square root, so we're probably going to have to stop there. Of course, ultimately what we're going to do is we want to make these pieces as small as possible, right? We want to take each of these delta x, delta y and shrink them down, because instead of looking at a curve this big, what if you looked at a curve that big? That is much closer to a straight line than that. In fact, the smaller the piece of an arc that you pick, the more it's going to resemble a perfectly straight line. So we are going to take these delta x and delta y's and we are going to make them as small as possible. You could even say that we're taking the size of each of these pieces and we're growing them infinitely small, right? We're bringing them very, very, very small. And so what happens when we shrink these infinitely small and infinitely small here is it lets us rewrite this in terms of an integral, because an integral sums up infinitely small pieces. A couple of things to realize. When delta y over delta x is infinitely small, we can write that as f prime of x, right? Now it's a derivative which is exact, and if this is infinitely small, then it is the exact slope. And second, we're going to go ahead and change our delta x sub k. Instead of being something tangible like a width of 2 or 1, it's going to be the smallest width possible, which is what we write as dx. So this whole piece up here is pretty nicely rewritten using an integral. And now we have a really nice formula that will let us find the length of any arc, any curved graph or straight line graph if you would like, and that's pretty powerful. We're able to use calculus to say no matter how curvy that thing is out there, if we have an equation, we can find its length. If we don't have an equation, we could approximate its length. Okay, so this formula should be memorized. Okay. Looking at this formula is good early on. We're actually going to see arc length again next semester, but not really much until then, so we'll keep practicing the formula, but when we see it next semester, because you'll practice it so much this semester, it'll be ingrained in your mind, and the next step where we go with it from there will make a lot of sense to you. You should note that f of x should be continuous there too, right? If it's not continuous, then you take the derivative, weird things happen, and then you have to integrate this derivative that's going to be all over the place, it's not continuous, strange things happen. So continuity is more than suggested, it is required. Okay, so We're going to go ahead and find the length of a curve here. However, there's a pretty major typo on this, so we should probably take a peek at it first. Instead of f of x equals 3 halves x to the 1/2, what I really meant to say was f of x equals x to the 3 halves. We'll see where that formula came in just a bit. And they're going to want us to find the length of that arc on this interval. So how do we do it? Well, we should probably notice that this formula over here uses f prime of x, and since it uses f prime of x and I have f of x here, my very first step is I'm going to find f prime of x. Okay, so f prime of x, that's going to give us 3 halves x to the 1/2. And actually, that's what this formula up here was supposed to say. I just left off the prime, and that makes things real weird. So we'll just do it like this, and I'll be better next year, and hopefully your paper will say the right thing. So either way, we end up here. We're very excited for ourselves. Let's go ahead and get rolling. In order to find my arc length on this interval, we need to take the integral from 0 to 4, right? That's my interval here, and we're going to use our formula. It's going to be our 1 plus f prime of x. I know what that is accurately now. 3 halves x to the 1/2 squared. Just using our formula, and of course I should probably remember the dx here. Let's start cleaning things up. You are going to want to write pretty small here. I'm going to definitely make use of my infinite paper, so I apologize for that. 0 to 4, we end up with 1 plus this square, because there's only multiplication. Let's square everything inside. 9 divided by 4, and when you combine your square and your square root, your square and your 1/2, it just becomes x. Okay, nothing too bad there. Oh, look, and they even gave us a friendly little hint. They said, let's try a u substitution. So let's. We're going to go ahead and substitute our u equals 1 plus 9/4 x. That's going to give me a du of 9/4 dx. Derivative of x is 1. We get a dx out there. However, we have integral or limits of integration. We should probably use those as well. So u of 0 is going to be 1 plus 9/4 by 0, which is 1. It's an easy one. And we also have u of 4. It's going to be 1 plus 9/4 by 4. 4's cancel. 1 plus 9 is 10. Okay, I think we have our new integral now. Our new integral will be the integral. Don't forget that there's still a square root. We don't need to make it that large though. And instead of this dx, which I forgot at the end, let's start replacing things. First, endpoints, that's easy. 1, 2, 10. The interior of the square root becomes u. The exterior, oh wait, well it says we can only replace 9/4 dx, and I just have a dx out here. I should probably do that cool game where we multiply by the reciprocal. 4/9 du is dx, and so this becomes 4/9 du. Cleaning this up a little bit, let's factor out the 4/9, no reason to complicate things, and let's rewrite the square root as that 1/2 power. And we can actually perform some fundamental theorem of calculus stuff. Add 1 to the power, that's going to be u to the 3 halves, 2/3 to offset that from 1 to 10, and then we substitute everything in. Oh no, wait, let's go ahead and divide or take out this 2/3 and combine it with the 4/9. That's going to give me 8/27, and then we'll substitute things in. 10 to the 3 halves minus 1 to the 3 halves, and I think you'll see that that matches our answer down below. Now, looking at a problem like this should inspire a little bit of worry into you because there was a decent amount of work there, but I actually do have some good news, and there really isn't a catch to this good news either, shockingly. On the AP exam, it's actually extremely rare that you have to find the length of a curve by hand. Usually the problems fall into two categories. One category is use a calculator once you've set up the integral to find the length, or part B is just recognize what equation is being talked about. And I'll show you a quick example for each, but you really should tackle these. There are 11 problems here. You should tackle these ones on your own. They're nothing too crazy. And if you need help, you can always check my solutions. They're posted on Teams. You can email me, ask me any questions you need. The reason you normally don't have to do this by hand, though, is because this function's stuck inside of a square root, and although we used a really nice easy function, x to the first power, if it was really any other function, a squared, a cubed, anything like that, we'd have been stuck. The antiderivative would have been really, really tough. And in particular, you see a lot of these with trig functions too, because they expect you to use your trig identities. When I say they, though, I really mean either the textbook or non-AP people, because I haven't seen you required to remember a trig identity on the AP exam since before 1997. So that's like, 23 years now. So trig identities, not a big thing on the AP exam. Should you know them? Absolutely. Does your textbook, and I think all textbooks require this, require you to use some of them? Absolutely. However, do I have any here? Nope, because we're practicing for that AP exam. So I promised you 2 quick examples. It's real easy. So 1a, write the integral for the length of the curve. You'll probably want a separate piece of paper for this. I'm just going to use the space up top right here. Well, we have f of x. Clearly, f prime of x is 2x. Okay, so the length of the curve is going to be from 0 to 2 square root 1 plus the derivative squared dx. And if this was a multiple choice answer, they would almost certainly clean this up a little bit and rewrite this as 4x squared dx. Okay. This would be a pretty tricky problem to take the antiderivative with without something that's called a trig substitution, which you don't have to know, or a calculator. That takes care of A. B is all about the calculator. Literally type this into your calculator, you'll find your answer. Very exciting. Okay, that would fall under the category of a calculator active question. What does recognize the equation look like? Well, this is one like problem 2. They give you the length of a curve, and they say, well, what function is this finding the length of the curve for? Well, let's take a look at this. If this is arc length, then we should be able to rewrite this. Let's do it the other way. We should be able to rewrite this as 1 plus f prime of x squared dx. And it's not quite there because this doesn't have a square. So let's rewrite it. 1 to 4 square root of 1 plus what thing squared gets you 9x to the 4th? Well, what squared? 3 gets you 9, and x squared gets you that. Now, we're not done here because our formula talks about f prime. But what we were able to do by rewriting it is now we can see that f prime of x is 3x squared. Okay, well, they want the actual function f, so just take your antiderivative. When you do the antiderivative, you're going to get x cubed plus, oh yeah, plus c. Don't forget that plus c. It's probably the most heavily memed part of calculus, right? Forgetting about that c. And I think this is our general function. General, right, because of that c. But that is what we found the length of the curve for. C just moves it up and down, so it doesn't matter what c is here. The length is still going to be the same. And then b just plays off of that. If the curve contains this point, then what's the actual equation of the curve? No longer the general, but what is the actual equation? Let's just plug things in. So we know the output is 6, we know the input is 1, and we don't know c, right? I just took what was here. So 6 equals 1 plus c, c equals 5, which tells us that the actual equation for this curve, which passes through 1, 6, is x cubed plus 5. The rest of these offer various twists and tricks on the same theme. Again, try them, look at your answers, ask me if you have questions, keep being successful, review and attest for the rest of this week. You're awesome. Keep up the great work.